Welcome to Study Loop.
So here we can find the angular acceleration for part A. This would be equal to the change in angular velocity with respect to time. This would be 0 minus 150 revolutions per minute divided by 2.2 hours multiplied by 60 minutes for every hour. And this is giving us negative 1.14 revolutions per minute squared. At this point, part B, we can use equation 1013. And essentially, t is going to be equal to, again, 2.2 hours multiplied by 60 minutes per hour. This is giving us 132 minutes. And we can say that delta theta would be equal to omega initial t. We know that this is going to be 0. Or rather, in this case, this is going to be the 150 revolutions per minute, because we're trying to see how many revolutions it goes through, essentially, until it comes to a stop. Plus 1/2 alpha t squared. This is going to be equal to 150 revolutions per minute multiplied by 132 minutes. And then this would be plus 1/2 times negative 1.14 revolutions per minute squared multiplied by 132 minutes quantity squared. And we find that delta theta would be approximately 9.9 times 10 to the third revolutions. So this would be our answer for part B, our angular acceleration for part A. For part C, we know that the radius is equaling 500 millimeters. So we can say that the tangential acceleration would be equal to the angular acceleration multiplied by the radius. This would be equal to negative 1.14 revolutions per minute squared. We're going to multiply this by 2 pi radians for every 1 revolution, multiplied by 1 minute for every 60 seconds, quantity squared, multiplied by the radius of 500 millimeters. And we have a tangential acceleration of negative 0.99 millimeters per second squared. For part D, we want to find the angular speed of the flywheel. So we can say that omega would be equal to 75 revolutions per minute. And then we're going to convert 2 pi radians per second, or rather 2 pi radians per every 1 revolution, and then 1 minute for 60 seconds. And this is giving us 7.85 radians per second. With continuing on for part D, with r equaling 500 millimeters or 0.5 meters, we can find the radial acceleration. This would be equal to omega squared times r, and this would be 7.85 radians per second quantity squared multiplied by 0.50 meters. And we have a radial acceleration of approximately 31 meters per second squared. We have to round to 2 significant figures. We see that the radial acceleration is much larger than the tangential acceleration. And so the magnitude of the acceleration would simply be equal to a sub r squared plus a sub t squared. And this would approximately be equal to simply the radial acceleration, and then again approximately equal to 31 meters per second squared. So when finding the magnitude, the tangential acceleration is so small that it doesn't really contribute to the magnitude at all. That is the end of the solution. Thank you for watching.